Welcome to Signal Processing Laboratory. So in this video we are going to see the 8th experiment, multiple input, multiple output. So the multiple input, multiple output is an antenna technology for wireless communication in which multiple antennas are used in both the source, that is the transmitter side, and destination, that is the receiver side. So the antennas at each end of the communication circuit are combined to minimize the error, optimize data speed, and improve the capacity of radio transmission by enabling data to travel over many signal paths at the same time. So here we are using multiple antennas at the input side and multiple antennas at the output side, so that we can combine this circuits to minimize the errors, optimize data speeds, and to improve the capacity of radio transmission. So we have seen this multiple input and multiple output antennas in many of the applications like receivers or Wi-Fi receivers, so where multiple antennas are used, and Wi-Fi transmitters. So in many applications we are using multiple antenna in the transmitter side and the receiver side. So creating multiple versions of the same signal provides more opportunities for the data to reach the receiving antenna without being affected by fading. So when we use the multiple versions of the same signal, so at the receiving side we can receive the signal without the fading effect, which increases the signal to noise ratio and the error rate. So by boosting the capacity of radio frequency systems, this multiple input and multiple output creates a more stable connection and less congestion. So the multiple input, multiple output systems are increasing being adopted in communication systems for potential gains in capacity. They realize when using multiple antennas. So the potential gain capacity is increased in this multiple input and multiple output. So multiple antennas use the spatial domain in addition to the time domain and the frequency domain. So without using bandwidth requirements of the, without changing the bandwidth requirements of the system. So we can, when we use the multiple antennas, we are including the spatial domain along with the time and frequency domain without changing the bandwidth of the system. So for a generic communication link, this example focus on a transmit diversity, that is the traditional receive diversity using the flat fading relay channel. It illustrates the concept of orthogonal space-time block coding, so which is employable when multiple transmitter antennas are used. So it is assumed here the channel undergoes independent fading between multiple transmit and receive antenna pairs. So here we are assuming that the channel undergoes multiple fading between the multiple transmitters and receiver antenna pairs. So for a chosen system, it is also provides a measure of performance degradation when the channel is imperfectly estimated at the receiver compared to the case of perfect channel knowledge at the receiver. So using diversity reception is a well-known technique to mitigate the effects of fading over the communication link. So we are using the diversity reception, so it is a well-known technique to reduce the effect of fading in a communication link. However, it has mostly been relegated to the receiver end. So the system proposes a transmit diversity scheme that offers similar diversity gains using multiple antennas at the transmitter. So this was conceived to be the more practical, as for example, it would only require multiple antennas at the base station in comparison to the multiple antennas for every mobile in a cellular communication system. So this section highlights the comparison of transmit versus receive diversity by simulating coherent binary shift keying modulation over flat fading relay channels. So in this program we are going to compare the transmit versus the receive diversity by simulating the coherent binary phase shift keying modulation over a flat fading relay channel. So for transmit diversity we use two transmit antennas and one receive antenna, while for receive diversity we employ one transmit antenna and two receiving antennas. So the simulation covers an end-to-end system showing the encoded or transmitted signal, channel model, and reception and demodulation of the received signal. It also provides no diversity link and the theoretical performance of the second order diversity link for comparison. It is assumed here the channel is known perfectly at the receiver for all systems. So we will simulate this program here. So this is the program for multiple input and multiple output. So let's execute it. So the output displays the transmit and receive diversity here. So the bit error rate results are given here. So to compare the different transmit and receive diversity. Okay, let's see the next experiment in the next video. Thank you.